And here we are again for the 10th time. Thank you all for sticking through this video series. For those of you who are new to the channel, in the last 9 videos I have described an esoteric programming language called Funciton, which I invented. I went through every excruciating detail on how the language works and how to write code in it, and the library of functions that I wrote for it to make programming in it less painful. Today's video is going to be different. Today I'm not going to talk about how to write the code. Today I'm going to explain how the parser and the interpreter work. In other words, how does Funciton code actually execute? Now before we begin, let me fill in a little gap that was missing from the previous videos. What you see here on screen is the question mark function, which we use to implement some kind of if-then-else. You know that it takes 3 parameters: the condition, what we want to happen if the condition is true, and what we want to happen if the condition is false. Now this function uses a comparison with 0 to determine if something is true or false, where we just consider 0 to be false and literally every other value to be true. But there are many cases where we already perform some kind of comparison, like greater than or less than, in which case the result will always be 0 for false and -1 for true. In cases like that, the comparison with 0 in here is completely redundant. Of course, our trusty factorial function is a perfect example of that. We already have a greater than here, which will always output 0 or -1. So I've replaced the question mark function with a new one. As you can see, I've used the interrobang character to name it. And here's what the function looks like. You can see that it's basically the same function, except that this comparison with 0 simply doesn't exist. We just use the condition value as is. Now, this means that the function assumes that the value is either 0 or -1, which means that if you put something else in, it'll behave weirdly. So we need to be careful to use it only on inputs that we know to be either 0 or -1. So let's take a look at this Funciton code and see how the parser deals with this. First, we have the factorial function, now with the interrobang function as I described. And then we have the greater than function, which the factorial function uses. We have the wire crossing function, which we need to cross 2 wires. And of course we have the interrobang function, which I just described. Now for the main program, I'm going to start with a very simple example, which literally just calculates the factorial of 1, which is obviously 1, but I will move on to a more elaborate example later. I've included down here the filter function so that I can show you how the parser deals with lambda expressions. And this is the string split function, the one that turns a single string into 2 strings based on a single separator. I'm showing you this function because it has more than one output. Now obviously at the start this is just a text file using Unicode box drawing characters, so let's draw a little grid to show the individual characters. But in order to deal with these characters more easily, I'm going to write 4 little functions which allow me to subdivide each character into the 4 lines that it consists of. I'm going to call them top line, right line, bottom line, and left line, and each of one will tell me whether it is a double line, a single line, or no line at all. So the first thing we want to do is discover all the boxes, and of course to do that we just go through the source code from top to bottom. And what we're looking for more specifically is the top left corner of a box, which is one where the top line and the left line is none, and the right line and the bottom line is not none. But of course that doesn't just tell us that it's the top left corner of a box, it'll also tell us what kind of edge the top edge of the box is and the left edge. So we can easily trace out the top edge of the box by just moving to the right and making sure that the left line and right line is what we expect, until we reach the point where that is no longer the case. And now we need to check that this is a valid top right corner of a box, which we do by making sure that the top and the right line are actually none, so it's not a T-junction, and the bottom line is something other than none. Now of course that bottom line can be anything, but once again it tells us what the right edge of the box needs to be. And then of course we do that for all 4 edges and we have a box. Now I want to quickly point out that any line that protrudes out of the box is completely ignored by this process. We're only looking at right line and left line when looking at the horizontal edges, and of course top and bottom for the vertical ones. So at this stage it wouldn't even notice that the bottom line in this example is not none. Okay, so now we have our first box. We now know the width and the height and the x and y position, and we know what types of edges they are. We need to deduce from that what kind of box it is. Now for many boxes we can do that simply by counting how many double edges it is. For example, in this one here we have a single double edge, so we know that that must be a lambda invocation. Remember that the Funciton syntax allows us to put that double line anywhere. It could be on the top or the left. I just always put it on the right by convention. Similarly, anything that has 3 double lines must be a lambda expression, no matter where the single line is. And something that has 4 double lines must be a literal. Okay, but back to our original example, we had a box with 2 double lines. Now this could be a declaration box or a call. How do we discern these? Well, the way I do it is we look at the first 2 if they're different, and the second and the third if they're different. If both of those are true, then it must be alternating between single and double lines, so it must be a declaration box. And anything else with 2 double lines must be a call. Now I want to quickly point out that this process will also find boxes like this one, where there aren't any double lines. But this isn't really a box, is it? This is a NAND and a splitter. So whenever there are no double-lined boxes, we just discard that. We don't process it as a box. Okay, now let's back up a little, back to our first box. Now that we know the position and the size of the box, we can look at lines that protrude out of it. Eventually, we want to trace out all of those lines to see what other boxes they connect to. So for the moment, we're just going to remember all of these in a list of unfinished edges, which I'm going to mark with these red arrows here. This call box, of course, has 3 of them, 1 on each side, but the parser will throw an error if there is ever more than 1 on the same side, because that's not allowed. And of course we do that with all of the boxes. But as the parser goes through the file, it will eventually get to this comment at the bottom. And you'll notice that there is a box inside of that comment. We don't want this algorithm to recognize that as a box, because it's inside of a comment. We need the parser to ignore the comment. Now, boxes that are double-lined on all sides, we've previously marked them as literals. So at this point, if there are no outgoing lines and the box is a literal, then at this point we can correct that and notice that it's actually a comment, and we can simply blank it out with spaces. So now the contents, including that box that was inside of it, will not bother it. And then we continue with the rest of the file and find all the boxes after that. And that concludes the first pass through the source code. There are only 2 other things that the source code is allowed to contain besides simple lines. T-junctions, such as this one, and cross-junctions, like this one. So we can do a second pass through the source code, look for all of these, create boxes, which aren't really boxes because they're 0 size, but we're going to put them in the same list with all the actual boxes. And then of course give them the red arrows or the unfinished edges. Now if we look back to that box that we saw earlier that isn't a box, you will see that it now consists of 2 T-junctions, which is exactly what we want. So that concludes the second path through the source code. At this point we've discovered all of the boxes, all of the T-junctions, and all of the cross-junctions. Besides that, the source code is only allowed to contain single lines. So any other characters that it finds in the second path, it will just throw an error. Okay, now let's look at what we do with these unfinished edges. Let's take this one here as an example. Since we know at this point that the source code contains only simple lines, we know that every character is going to have only 2 out of the top line, right line, bottom line, and left line, and they're always going to be single lines, because anything that's not like that, we will have already complained about. So we can easily just follow the line until we hit another unfinished edge, and then we just remove those 2 and turn them into a finished edge, or edge. Most of the unfinished edges are going to run into another unfinished edge at the end of the line, but there are some that won't, like this one here. Because if we follow that line, we eventually encounter a dead end. Now, you know that the dead end is actually the output of the function. So at this point, not only do we turn the unfinished edge into an edge, we also create another 0 size box representing the output of the function. Once we've done that to all the other unfinished edges, we now have all the boxes and all the connections between them, so at this point, we don't need the Unicode characters anymore. So let's get rid of the grid. The next thing that we need to do is to determine what direction each of these edges is pointing, because we need to know which direction the data is flowing, we need to know which lines are inputs and outputs to the function calls, etc., etc. So let's take a look at this. First of all, here are some literal boxes. Well, literals never have inputs, so all of the lines that point out of literal boxes are always lines that point away from that box. The same is true of declaration boxes. Everything that comes out of those boxes is a parameter to the function, so nothing goes into these boxes. Of course, the output nodes that we added whenever we encountered a loose end, they're kind of opposite. No data comes flowing out of it, it all goes into it. Now let's take a closer look at this function declaration here. Well, just from the declaration box and the output box, we can see the relative orientation of the parameters which come out of the declaration box and the output which goes into the output box. So if you want to call this function, then the output, the value that comes out of the call box, might point in the same direction as the output in the declaration. But then the first parameter, which is coming out the left of the declaration node, because it is pointing leftward, will go into the right side of the call node, so that it flows in the same direction. And similarly, the second parameter pointing to the right will go into the left of the call node. But of course we all know that Funciton is rotation invariant, which means that a call to this function can have any one of 4 different orientations. So we need to take that into account when determining which edges are the inputs and which ones are the outputs. Now in this example that is not hard, because the top of this call box has no line at all, and that already rules out 3 of the 4 possibilities, so we can immediately deduce the direction of the other 2 arrows. But here's an example where it's not that simple. We can only rule out 2 of the 4 combinations, so we need to hold on to that box and then loop back to it later. And once we come back to it later, maybe we will have deduced another box like this one here, and that will allow us to deduce which of the 4 orientations it is. There is an interesting thing that happens with boxes that have 2 inputs and 2 outputs, such as, for example, a lambda invocation like this one. Let's say we've already deduced one of the arrows, in this case the arrow going in from the bottom. That will allow us to rule out 2 of the 4 orientations. But even if we don't know which of the other 2 orientations is the right one, we can see that they have something in common. They both have an arrow pointing up. So we can actually make a deduction, even though we still need to keep that box in the loop and come back to it later. And finally, there are T-junctions, which are the only ones that have actually 8 different possibilities, because it could be either a splitter or a NAND. But as you already know, just from the orientation of the T-junction, we can narrow this down to 2 possibilities. Okay, so now you know how we deduce the direction of every arrow. Now, up to this point, all of the objects that we've been dealing with are kind of 2D geometrical things, right? We have boxes where we know a position and a size, but obviously when we execute the program, we don't really care about those. So the next pass is going to convert everything into something that is just more useful for execution. Let's start by grouping everything. I mean, we currently have a long list of boxes and a long list of edges, but we kind of want to know which boxes belong to one function declaration. So we're just going to recursively follow the edges and put everything that belongs into one function declaration into one list. And while we do that, we can make sure that every function declaration only has one declaration box, because if it has multiple, then we need to output an error message. Okay, now let's take a closer look at the factorial function. Now, to convert all of the boxes to the useful nodes, we're going to start at the bottom, at the output node. Why we do that, you'll see later. Ultimately, what we want is for every node to point at the previous node. In other words, all the pointers need to point in the opposite direction of what you as the Funciton programmer would find intuitive. So to represent that, I'm just going to swap the direction of every arrow right now. Now think about what the final result of the factorial function is going to be. That's right, it's the result of the interrobang function, the if-then-else. So we need a pointer pointing to that. Now we're going to create a 4-element array in which every element represents a direction, but the factorial function has only one output, so we're going to put our pointer in the correct position and all the other elements are just going to be null. Meanwhile, in the string split function, which as I mentioned I included because it has multiple outputs, one of the outputs is going to end up in the first slot, just like before, but the other output, which is pointing to the right in the original source code, is going to go in the 4th slot. And so we end up with 2 pointers and 2 nulls in the array. Now let's see what we need to do with function calls. Now in this case here, we have the question mark function, which has only one output, so we're going to create a node that represents that output. But of course there are some functions like the wire crossing function here which have multiple outputs. So we need to create a separate node for each output, and they need to remember which direction they pertain to. Now here's another wire crossing function. Let me just add the output nodes. And now you might reasonably ask, wait, why are these arrows pointing in such wonky directions? Here they're pointing in the opposite direction from the green arrows, but here they're pointing in some weird other direction. Well, remember that every function call could be rotated any which way. The direction that we care about is the direction of the output in that function's declaration. So the wire crossing function has an output going down and one going to the right. And the purpose here is to remember which of our output nodes is which of these outputs. Indeed, you'll notice that every function that has only one output no matter which orientation it has, the arrow always points down, because that's just my personal convention that the output always points down when there is only one of them. Now obviously we need to deal not just with the outputs, but also the inputs. We need to know what value goes into each call. Well, for the inputs to these calls, we're going to do something very similar as we did to the outputs to the function. We know which values need to go into the call node, and we know which direction they have in the original declaration. So we can create a 4-element array, one for every call node, and once our recursive process which converts all of the other nodes comes back with a pointer, we can put that pointer in the correct place in that array. And we end up with an array with some null values wherever there isn't an input for that direction, and all the other ones are pointers to the input values. Let's turn our attention to a lambda invocation box. Well, a call to a function can have any number of outputs, but a lambda expression always has exactly 2 outputs. So we're going to name them 1 and 2. Now the lambda expression itself has only one input, but the lambda invocation box needs 2 inputs. One which will be the input to the lambda expression, and the other one will be what determines the lambda expression to call. Remember that lambda expressions are themselves identified by numbers, and we need to get that number from somewhere. I'm going to mark the input to the lambda expression with the letter x. So this time, instead of an array, we just have 2 separate pointers, because we always need exactly those 2. For lambda expressions is basically the same thing, but the other way around. The 2 things that come out of the box are the lambda expression and the input, and the things that go in are the outputs that the lambda expression generates. Now, of course, you remember that not all lambda expressions use both of their outputs, and we've learned that we use this kind of construct to silence an output. And similarly, we use the same construct to silence an input if a lambda expression only needs to generate a value and not use any input. So what do we do in cases like this? Well, it's very simple. We just don't generate that output node. Another thing that we need to deal with is, of course, the cross junction. You remember that the cross junction performs 2 different operations, the less than and the shift left operation. Now let's take a look at the less than operation first. Of course, it has one output, which is the result of the less than, but it has 2 inputs, which I'm going to call the left and the right operand. And this is not left and right as in the orientation in the source code, but rather the left operand is the one that needs to be evaluated first, so that we know which one is less than which other one. Now in this example we have the same kind of construct which silences the shift left output, so we don't actually need to worry about the shift left part. But if we ever encounter a cross node that actually uses both of those operations, well then we just create 2 separate nodes. Another thing we need to deal with is the declaration nodes, because some of them have multiple arrows pointing into them, and we need to know which direction, which input they refer to. So we simply create multiple nodes, 1 for each direction. And it turns out we don't even need the declaration boxes at all anymore, so I'm going to remove them. As for T-junctions, well, we can now tell from the orientation of the arrows which ones of them are NANDs. So this one, for example, is a NAND, so we can convert it to a node just like we did with the less than. And of course it needs a left and right operand, again because the order of operations is important. However, some T-junctions, like this one here, are splitters. They're not NAND. So we don't actually need to perform any operation here, so we don't need to represent these as nodes. So now you'll see why I kept emphasizing that when it's a NAND, it's an operation, but the splitter is just syntax. It turns out that we can literally get rid of the splitter. Instead of having 2 pointers point into the splitter and then have another pointer point away from the splitter, we can have those first 2 pointers point directly to where we want it to point. And here's a little secret, the same actually applies to the wire crossing function. We're going to get rid of that one as well, and we're just going to have the pointers literally just pass right through it. And if you're wondering, wait, are you special casing this function name? No, I'm not. We can look at the declaration for the function and we can see that the output is directly connected to the input in the declaration. Whenever that is the case, this optimization applies. And then we end up with a lot of pointers that point much more directly to where they need to go, and we have much fewer nodes that we don't need. And believe it or not, that's it. We've now successfully converted the input, which was just Unicode characters, into this in-memory representation, where you have these nodes, which are just tiny little objects, which have pointers pointing between each other. And now we can recursively go through them to execute the program. Let's see how that works. Okay, now that we finally have an in-memory representation of the nodes that we need to execute the program, Let's actually execute one. So I promised you that I would start with an extremely simple example, which is a program that just calculates the factorial of 1. The answer, of course, is going to be 1, which is going to be a non-printable character, so it's not going to show anything. But it's a good example to demonstrate all the principles. The parser will have made sure that there is only one program in the input files and that the program will have only one output. So we can just look at the 4-element array and we will find a single value in it that isn't null. And we can follow that pointer to the first node that we need to evaluate, which in this case is a call node that calls the factorial function. We're going to need to keep track of all the functions that we called in something that is called a call stack. And I'm going to visualize that call stack here on the left side of the screen. So the first thing that goes on our call stack is the factorial function. Now we can just look at our catalog of parsed functions and find the factorial function in there. For reasons that will become clear later, we're going to need to take a copy of that so that the original remains unchanged. Now, what is the final result of the factorial function? Well, remember that the call node remembered the direction that it references, and we can simply look that up in the 4-element array for the factorial function. So whatever that 4-element array pointed at, our call node is now going to point at. But what about the input node, in other words, the function parameter? I said earlier that we take a copy of this entire function, but that was kind of a lie because these input nodes do not get copied. Instead, the input node is itself associated with a direction which we can look up in this 4-element array, which is in the call node. And that will tell us what the input to the function is. So everything that pointed to the input node, we can just have it point directly at the value that is the actual input to the function. In this case, that is the literal with the number 1 in it. So in essence, the call node basically gets replaced with a copy of the function, and all of the input and output pointers point to where they need to go for this particular call. Okay, but let's not lose sight of the fact that we want to evaluate the factorial function, right? So we need to follow that pointer and evaluate the next thing that it points to, which in this case is the interrobang function. So we can look that up in our catalog and take a copy of that too. Now the interrobang function is a little bit hard to read, so let me remind you exactly how it works. It takes 3 inputs. The first one is the condition, which I'm going to call C, and it's either -1 for true or 0 for false. The second one is the yes value, what we want to have happen if the condition is true. And then of course the third one is the no value. Now the condition of course can be either 0 for false or -1 for true. And the way that the interrobang function works is that we use the NAND operator on that and the yes value. So if the condition was 0, well, NANDing that with anything will always give you -1, but NANDing -1 with the yes value will give you the bitwise negation of the yes value. And then besides that, we also NAND the negated value of C with the no value n. Now if the condition is 0, then we're actually NANDing -1 with n. So here we get the negated value of n, and if C was -1, it gets negated to 0, so this gives us -1. And now we're going to call these values A and B, and then we're going to calculate A NAND B. And in the first column, this is going to give us -1 NAND the negation of n, so that will negate the negation of n again, so it gives us n. And in the other case, we're doing the same thing with y, so we end up with y. And now you can see that if the condition is 0, in other words false, we get the n value, the no value, and if it's true, we get the y value or the truth value. In the actual implementation, this is where we calculate A. This is where we negate C. This is where we calculate B. And this is where we calculate the final result by NANDing A and B. So let's connect up the output. And as for the inputs, well, this time there are 3 different ones. They are, of course, C, Y, and N. But we also have 3 different values in our array where we just look them up. So everything gets connected up correctly. Now once again, in order to evaluate the interrobang function, we look at its output, and its output is of course the NAND that calculates A NAND B. So we're gonna need to put that on the stack. And then in order to evaluate A NAND B, we first need to know what A is. So we look at the first operand, which is the left operand, and of course that takes us to another NAND node. So once again, we need to look at the left operand, which in this case is C. Now as we follow the pointer to that C node, we find that it takes us to this call to the greater than function. Now this call is of course not in the interrobang function anymore, we're back in the factorial function now, but the interpreter doesn't care. So once again, we need to put that function on the stack, and then take a copy of the function from our arsenal, and then join up all of the input and output nodes. And what we end up with is literally just a less than node, which is of course one of the built-in instructions. Now, if you're wondering why it's a less than node rather than a greater than, well, it's because the only built-in operation is less than, and in order to implement greater than, we're using the less than operation with the left and right operand swapped. So continuing on, in order to evaluate our call to the greater than function, we need to evaluate the less than operation, which we do by looking at the left operand first, and that one is the number 1. Now remember, that is the one from the main program, which was fed into the factorial function. This is the first time that we're seeing that. So this literal with the number 1 will literally return the number 1, and that will be passed into the less than operator, and it will remember it as its left operand and then move on to its right operand. So let's follow that pointer, and we get to the number 2, which is part of the terminating condition in the factorial function. Once both of those values are passed into the less than operator, it now has everything that it needs to calculate its result, and the result of course is -1, because 1 is in fact less than 2, so we want to return true. Now that value gets passed down to the call node, but the call node has nothing else to do. This is the final value for the call, so we just return that directly. So at this point we've calculated this C value, which is the left operand of this NAND. So let's remember it for later. And the other operand is of course Y, which is the value that we want to return in case the condition is true, which in this case it is. So we look at the right operand, and it's pointed at a literal 1. Now this is the 1 from the factorial function for the case in which the terminating condition is true. We want to return 1 for 0 factorial and for 1 factorial, so that's what we're doing in this case. So now that this NAND node has both of its values, it can do its calculation, and -1 NAND 1 is the bitwise negation of 1, which is -2. And this -2 is the value of A. Moving on to the right operand, which is B, we follow the pointer and we find that it's another NAND node. So we look at its left operand, and that is another NAND node. And then we follow its operand, and it takes us to the call node, which we've seen before. This is the call node for the greater than function. Well, you know that we've already calculated the value of C. And the way that the interpreter knows this is by actually remembering the result of every node. So the greater than function that we called remembers its result. It already knows that it is -1, so we can just return that directly. Now the right operand to this NAND is also C, because remember that's how we do a bitwise NOT, is by NANDing a number with itself. So the right operand will also point to the call node for the greater than function, and it will also return the same value that it has already remembered. And at that point the NAND has both of its values, so we calculate -1 NAND -1, which is 0. Now passing that down to the next node in the call stack, we find that we need N, which is of course the right operand for the NAND that tries to calculate B. So if we follow the pointer for that right operand, we get to a multiplication function. Wait a second, multiplication? This is part of the recursion for the factorial function. But we didn't want to do any recursion, did we? The terminating condition was true, we just want to return 1. Well, indeed, this is where the short-circuiting semantics for the NAND operator comes in. You see, this NAND node will notice that its first operand is 0, and then not even look at its right operand. So it will never even see the multiplication node, it will just return -1 immediately. And now our final NAND has all the values that it needs, so it calculates the result, and the result is 1. As before, that value is just passed down by the interrobang call, and then by the factorial call, and then it ends up at the bottom of the call stack. So when the call stack is empty and we have a value that we don't know where to put, then that value is our final answer, in other words, the output of the program. Now for my next example, I want to show you how a function works when it has multiple outputs. And as I've already hinted, I'm going to use the string split function. So let's write a very simple program that uses it. We're going to start with standard input, and we're going to pipe that input straight into the string split function. But what do we want to split by? Well, let's just use the comma, which is Unicode character number 44. And then the string split function is going to return 2 strings, so to make sure that we can actually see both of them in our output, let's concatenate them. But I'm going to intentionally join them up in such a way that the first string that comes out of the string split function is going to be the second argument to the concatenation function. Remember that the arguments are in counterclockwise order starting from the output, so this one here is actually the first input to the concatenation. So if we run this program and provide it with a string a, b, we expect to see ba without the comma, and that is indeed what we get. Now let me quickly remind you how the string split function works. It is of course considerably bigger than the interrobang function, but it's not that much more complicated. The first thing that we need to do is we need to find out if the separator even exists in the string. And we do that by using the index of function. So this will return -1 if the string is not found, or otherwise it will find the index of the string. So in our example where we have a, b and we're looking for the comma, this will return a 1. But of course we need to check if it returned -1, which we do with this comparison here. Now again, remember that the output is at the bottom, so this is actually 0 less than or equal to the index, which is the same as saying the index is greater or equal to 0. So we use the interrobang function to look at the result of that, and if the result was -1 and the separator is not in the string, then we just want to return an empty string as the second result, which is why there is a 0 here. But in all other cases, including the one that we have, we need to chop off everything from the start of the string up to the end of the separators. So in our case, we need to chop off the a and the comma. How do we chop off characters? That's right, we shift right by a number of bits, which is 21 times the number of characters, because every character is 21 bits. And how many characters do we need to chop off? Well, the index of function already told us where the separator starts, so we need to chop off everything up to there. But then we also need to chop off the separator itself, which is why we have the length function here to determine the length of the separator, and then we add those two together before we multiply with 21. And that gives us the second string that we want. In the case of the first string, which is what this conditional here is responsible for, we use a bitwise AND to remove everything starting from the separator. So we only need the index at which the separator occurred, we need to multiply that by 21, and then we need to create a number that has that many 1 bits, and then if we bitwise AND with that, it will keep only those characters. So let's see how the program operates. Of course, just as before, we're going to look at our catalog, find only one main program, look at the 4-element array, find only one value that isn't null, and hey presto, it points to a call node. Now, this is of course a call to the string concatenation function, which is not the one that I want to go into detail here. But it does end up on the stack, so I'm going to pretend like it's a built-in, so I'm going to use a green box instead of a blue one to represent it, and I will move straight on to its first operand, which is of course the call to the string split function, but more specifically, it is the right-pointing output. So same as before, we're going to take a copy of the entire function, except that we're going to join up the inputs and outputs correctly. And then we look at the pointer that the output now points to, and we find that it points to an interrobang function. Now, we already know how the interrobang function works, so again, I'm just going to pretend like it's a built-in. And the first thing that the interrobang function needs to evaluate is, of course, its condition. Now, the condition for this interrobang is, of course, whether the separator is in the string, in this case our comma, which we do using this less than or equal to operation. And as I've already hinted, the first argument to the less than or equal to is the 0, and the right argument is the result of the index of operation. Now, of course, the index of operation needs to know what strings to operate on. So this is the first time where the interpreter actually gets to the standard input node. So it is at this point that it'll read the entire input string, convert it to the 21-bit string encoding that Funciton uses, and then returns that as a value. Now, that value is of course a large integer, but I'm going to show the string so that you can follow along what's happening. So where it says a, b, it's actually the integer that encodes the string a, b. The other argument to the index of function is of course the 44, which is the Unicode value for the comma. And I'm going to assume here that the index of function works correctly, and it will tell us that the comma occurs at index 1, so it returns the number 1. And then that number is of course passed into the less than or equal to, which will notice that 0 is in fact less than or equal to 1. In other words, the comma did occur in the string, so it'll return true, or -1. Okay, so that is the condition for the interrobang function, which is of course true. So the interrobang function needs to look at its yes argument. So we now go through the calculation necessary to chop off the a and the comma. And we chop off characters by shifting something to the right. What do we shift to the right? Well, the input, of course, a, b. And by how much do we shift it to the right? Well, we need to multiply something by 21, so there is a multiplication. And we need to add the index of the separator to the length of the separator, so there is also an addition. Now, the first argument to the addition is, of course, the index of, which we've already calculated in our less than or equal to condition. So the call node remembers its value and just passes it out. Following the other argument of the plus function, well, it takes us to the length function, which again, I'm just going to assume that it works correctly, and its argument is of course the separator, which is the comma, so the length of that is going to be 1. 1 plus 1 is of course 2, so that gets passed down to the multiplication, and the other argument to the multiplication is the 21, so we end up with 42. And you already know what's going to happen next. Shifting right, the a comma b is going to chop off the first 2 characters, which is going to leave us with b. The interrobang function takes that as its answer, and so the result for our first call is b. Now I want to take a quick moment to emphasize here that this process has only evaluated as much of the function as we actually needed. You'll notice that all the nodes in the left half of the function, the one that calculates the first output, weren't even touched. So that way, if you call a function with 2 outputs but you need only one of the outputs, it doesn't actually do any redundant calculations. The b that we got gets passed to the string concatenation function, and then of course we will evaluate its other argument, which is the other output node of the same function call. So at this point we don't do another function copy because we already have the function in there, but this time the output to that call is a different node. In this case it's the interrobang call on the left. Now of course the condition to the interrobang function is the same as before, and we've already calculated that. So the -1 that we already have just gets reused, and the interrobang function immediately looks at its yes value. Now in this case the yes value is a bitwise AND, so to abbreviate that I'm just gonna pretend that is one operation. And the left operand to this AND is this familiar construct in which we use a shift left and a bitwise NOT to construct a number that consists of a certain number of 1 bits. So again, I'm just going to pretend like that's one operation. But of course we need to know how many 1s to generate, and that requires a multiplication. The first argument to the multiplication is of course the result of the index of, which tells us how many characters are in the first string before the separator. And once again, we already know the value from the previous invocation, so we can just reuse that. The second argument is the number 21, so we do the multiplication, we get 21. And then at the end of this construct, we have a binary number consisting of 21 1s. And that gets passed to the bitwise AND, and the right operand of that is the standard input node, which also already knows its value because we've already evaluated standard input. It's of course the a comma b string. So the AND operation will reduce the string to just one character, which in our case is a. And that gets passed down to the interrobang function, which just passes it through, and then the string split function, which also passes it through. So it ends up the second operand to the string concatenation function, which of course concatenates the 2 strings, and so we end up with BA as our final answer, the same as what we saw in the console earlier. And as my third and final example, I want to show you something that involves lambda expressions. Now at the start of the video, when looking at the parser, I used the filter function for lazy sequences to show you how the parser deals with lambda expressions. But to keep this example simpler, I'm going to use the filter function for lists. Specifically, I'm going to start with a list containing the numbers 4 and 7. I'm going to apply the filter function with a lambda expression that checks if a number is odd. And since 4 is even but 7 is odd, I expect to get a list out that has only the 7 in it. To do this, let's first write some code that actually generates the list containing a 4 and a 7. So let's start with an empty list, which is of course represented by the number 0. And then let's use the unshift function to add the element 7 to it. And then we just use the unshift function again to append the 4 to the start. And finally, since we want to use that number in our source code, we need to be able to see it, so I'm going to convert it to a string for output. And now if I run that program that we just wrote, we get this large number, which we can just copy and paste. So the program that I actually want to show you starts out with this list containing 4 and 7, which we represent by that large integer. And then we want to run that through the filter function. And then we want to pass a lambda expression into the filter function. And the 4 connectors in counterclockwise order are lambda expression, input, output 1, and output 2. Now we only need output 1, so for output 2 I'm just going to put a 0 there. And as for output 1, well, we want to check if a number is even, right? So how do we do that? we do a bitwise AND with the number 1. If the result is 0, then the number is even, so we want to filter it out, and if it is odd, then the result will be 1, which is not 0, so it will be considered true, and so the odd numbers will remain. Now, as before, the resulting integer will not be a readable Unicode string, so I'm going to convert the integer to a string so that we can read it. Now, if I run this program, I expect to see some large number, and it turns out this number is correct, but we don't really care about this number, we care about how the program executes. So, let's take a look at that. So here's what the program looks like after parsing. Of course, the literal at the top is still just a large number, but I'm going to add an annotation there so that you know that it represents a list containing a 4 and a 7. As before, we find the only pointer in our 4-element array that isn't null, and it points to the function that converts integers to strings. So let's just put that on the stack. And then we get straight to the filter function, which is what we're here to see. So after taking a copy of the function and joining up all the inputs, this is what it looks like. And of course the first thing that the output points at is this question mark. Now this question mark tests if the list is empty. This is the terminating condition for the recursion. If the list is empty, then we're done. But in our case, of course, the list is not empty, so the question mark function will see a non-zero value and it'll interpret that as yes. So I'm just going to mark that as a tick mark. Now the yes branch of the question mark points to another question mark. Now this is the one that runs the lambda expression and tests each element of the list. You can see that the condition for that question mark is in fact the lambda invocation. Now, like a function call, a lambda invocation gets added to the stack, but then of course it needs to find out what lambda expression to call, and for that purpose we follow the lambda pointer. In our case, the lambda pointer points directly at the lambda expression. Now obviously that doesn't always need to be the case, you can get the lambda expression number from anywhere, but in our case this is what happens, and the first thing that the lambda expression box does is it needs to allocate a number for this lambda expression. Now remember that I said that lambda expressions are counted from 1, so that you can still use the number 0 to indicate like the lack of a lambda expression. So every time a lambda expression box is evaluated, it creates a new value starting at 1, and then it puts a pointer onto a list of lambda expressions that the interpreter needs to keep track of. So all that happens for now is that the number 1, which is now the identifier for that lambda expression, travels back up that pointer and is passed into the invocation box. And then the invocation box needs to look at that list to determine what lambda expression to actually call. Now remember that when you call a normal function, we just copy the entire function declaration. In this case, we need to copy only the lambda expression. And we do that by taking the pointers for the outputs, and then we recursively take copies of every node from there. Cool, now that we have a copy of our lambda expression, we can do with it what we want. Well, first of all, at this point, we're only interested in output number 1, so we don't actually copy the output number 2 part unless it is actually needed. The output number 1 pointer is the one we're interested in, so we connect that up with the lambda invocation. But of course, the lambda needs an input as well, the pointer for which we can just look up here, and then we can just join that up. And now that everything is joined up, we don't need the lambda invocation and the lambda expression boxes anymore. We're now left with the meat of what the lambda expression is trying to do, which is a bitwise AND with 1. So I'm just going to put that on the stack. And once we get to the left operand here, the thing that we want to bitwise AND with 1, we find that it points to one of the outputs of this call to the shift function. Now let's just trust that the shift function works correctly, and for our original list with a 4 and a 7 in it, it will return a 4. Now since 4 is even, the bitwise AND with 1 will result in 0, and that 0 is passed down the stack and it becomes the result of that lambda invocation. We've now successfully evaluated the condition for the second question mark function. That condition turned out to be 0, so the question mark will interpret that as a false, so I'm going to represent that with an X. And since it's false, the next thing we need to evaluate is the no value for that question mark, which points directly to the recursive call for the filter function. So at this point, we're calling the filter function again, so we end up with a second copy of it. Of course, that second filter function still has a question mark on the bottom, which checks if the list is empty. Now you recall that in the previous invocation, this one pointed directly at the original list. Well, this time it is pointing at the second output of the shift function. So that should give us the rest of the list after the 4 has been shifted out. So that will give us a list containing the 7, which is of course not 0, so the question mark will see that as a true as well. So we get another tick mark. And then the yes branch of that question mark points to the second question mark, which will invoke our lambda again. Now remember that we're passing down the same pointer to the same lambda expression, so this time we're not allocating a new lambda expression. Instead, the lambda expression box remembers that it allocated the number 1 to this lambda expression. So it'll just reuse that value and pass it down to the invocation box. And then the invocation box takes another copy of the lambda expression just as before. And of course the lambda expression still does the same thing, it does a bitwise AND with 1, so I'm just going to represent that on the stack. And then the left operand it receives is, again, the result of the shift function. But this time the shift function looks at the result of the previous shift function, which is a list containing the number 7. So the result this time will be the number 7. Now, of course, 7 is odd, so the result of 7 and 1 is 1. And that 1 is the result of the lambda invocation. And it gets passed down to the question mark, which sees it as a true this time. So if we look at the yes branch of the question mark, we see an invocation of the unshift function. So this is where we need to reconstruct the list containing just the elements that we want. Now the first argument to the unshift function is of course what kind of list do we need to add elements to. So to get that list, we need to run the recursive call of the filter function a third time. Now remember that in the previous invocation of the filter function, the condition for the first question mark was the list containing the number 7, which was the result of that shift over there. This time is going to be looking at the result of the shift in the current iteration. And since that one has already shifted out the 7, the result this time will be an empty list, which is 0, which is false. And so the question mark for the third iteration will just directly return this 0. But that 0 of course represents an empty list, so I'm going to mark that as an empty list. So that empty list makes its way into the unshift function. And the other argument, of course, is the result of the shift where we obtained the element that we just ran through the lambda expression, which in our example is the 7. So we end up unshifting the 7 into the empty list, which gives us a list containing 7. Now you can see that everything else in the call stack is a call, which will just pass down that value as its return value. So at the end, that value makes it all the way into the function that is supposed to turn it into a string, and so a string representing that integer is our final answer. Now there is one complication that I glossed over. You see, lambda expressions are allowed to capture values from the outside. Right, you can use a value that comes from outside the lambda expression in the calculations inside of the lambda expression. And of course we don't want those calculations to be copied every time you call the lambda expression. So the kind of nodes that get copied when you copy a lambda expression are only the ones that depend on the lambda expression's input. And that's it! We're finally at the end of this very long video series. Thank you very much for sticking through everything. It was a delight for me to describe my programming language to you, and I hope that you found it entertaining, educational, whatever you get out of it, I'm happy. Now, as I already announced in my previous video, I intend to start a new video series in which I'm going to use Funciton to solve the problems in Advent of Code. Now, in the previous video, I mentioned Advent of Code 2023. But this video took me longer to make than I had anticipated, and you can see here that the website for Advent of Code 2024 is already online. So who knows, maybe I'll start with that. Thank you so much for watching, and if you enjoy what I do, consider supporting me on Patreon.